Hello everyone, this is Vaini Maditati. In this video, I am going to explain organic chemistry and we are going through classification and nomenclature in this video. I am going to explain introduction, structure and bonding of carbon in carbon compounds, writing Lewis structure and structural representation of organic molecules in this video. And we'll go through a few other topics related to this in my next coming videos. Firstly, while coming to the introduction, organic chemistry is the branch of chemistry which deals with the study of carbon compounds. The simplest organic compounds containing hydrogen and carbon only are called as hydrocarbons. First, we have to know what is meant by hydrocarbon. The simplest organic compound containing carbon and hydrogen only. These are called as hydrocarbons. And according to the vital force theory, organic compounds cannot be prepared in the lab artificially. Urea is the first organic compound prepared in the lab by Ohler. Ammonium cyanate on tautomerization gives us urea. We'll come to know about tautomerization in later. First organic compound prepared from its element in the lab is CH3COOH. It was prepared by Kolbe. And the second organic compound prepared from its element in the lab is CH4. It was prepared by Berthelot. CH3COOH is the first organic compound prepared by Kolbe and CH4 second organic compound prepared by Berthelot. And the ability of carbon atom to form long chains or ring is known as catenation. It's very important to know about catenation. Here, among all elements in the periodic table, carbon is the only element which has more catenation property. It shows the catenation property. It means the ability of carbon atom to form long chains or rings. Carbon is the only element among the periodic table which can form long chains or rings. And next, carbon compounds are innumerable due to four reasons. Let us go through the four reasons. The four reasons are maximum catenation capacity of carbon and tetravalency, isomerism in organic compound of carbon. What is meant by isomerism? The molecules which are having the same molecular formula but differ in their structures. These are known as isomers. And next, carbon has tendency to form multiple bonds. Due to this four, carbon compounds are innumerable. And next, structure and bonding of carbon in carbon compounds. Here the atomic number of carbon is 6 and its ground state electronic configuration is 1s2, 2s2, 2px1, 2py1 and 2pz0. The excited state electronic configuration of carbon is 1s2, 2s1, 2px1, 2py1 and then 2pz1. The energy required for excitation is 501.6 kilojoule per mole. And next, in organic compounds, carbon atom undergoes sp, sp2 or sp3 hybridization. Look at this table. Here in sp3 hybridization, the number of orbitals involved are 1 s orbital and 3 p orbitals. And percentage of character of orbitals. Here the percentage of s character is 25% and the p character is 75%. And the nature of bonds is here all are sigma bonds and no pi bonds exist. Bond angle 109 degree 28 minute and orientation of orbitals is tetrahedral. And while coming to the sp2 hybridization, here the orbitals involved are 3. They are 1 s orbital and then 2 p orbitals. Here the s character is 33.3% and the p character is 66.6%. Here the nature of bonds are 3 sigma and 1 pi and the bond angle 120 degree and the orientation of the orbital is planar. And while coming to the sp hybridization, here the number of orbitals involved are 2. They are one s orbital and then one p orbital, and the percentage of character of orbitals are, here each s and p consists of 50%, and the nature of the bonds is 1 sigma and then 2 pi bonds. Here the bond angle is 180 degree and the orientation of the orbitals is linear. And here you have to remember a point that greater the s character, lower the energy and thus near to the nucleus. That is, the orbital is smaller. See, when the s character is greater, energy is less. Greater the s character, lower the energy, and thus near to the nucleus. That is, when this is near to the nucleus, the orbital is smaller. And then the change in hybridization affects the electronegativity of atom. Let us see how the change in hybridization affects the electronegativity of carbon. When the s character is more, the electronegativity is also more. Greater the s character of the hybrid orbitals, greater is the electronegativity. Simply, percentage of s character is directly proportional to electronegativity of carbon. See here, the electronegativity of sp carbon is greater than sp2 carbon, greater than sp3 carbon. As the percentage of s character increases, the electronegativity of carbon also increases. If the percentage of s character decreases, then the electronegativity of carbon atom also decreases. This is the point to be remembered. Once go through this table after completion of this video, and if you have any doubts regarding it, ask in comments. You have to remember one point that for the formation of pi bond, parallel orientation of two p orbitals on adjacent atoms is necessary for a proper sidewise overlap. For example, in ethene molecule, both the p orbitals are mutually parallel and are perpendicular to the plane of the molecule. Here the rotation about CC bond in C double bond C is restricted. Now let us go through few examples regarding this topic. The first question: write the hybridized state of carbon in following compounds and shapes of each of the molecules. Before going to solve this question, remember this: if a carbon atom is attached to a double bond, then it undergoes sp2 hybridization, and if it is attached to a triple bond, then it undergoes sp hybridization, and if a single bond is attached, then it will undergo sp3 hybridization. See here, a triple bond carbon sp hybridization, a double bond carbon will undergo sp2 hybridization, and a single bond carbon will always undergo sp hybridization. Now let us go through this. CH2 double bond O. So it undergoes sp2 hybridization, and the shape of this molecule is trigonal planar. And while coming to the CH3F, here the carbon forms a single bond with 3 hydrogens and a single bond with fluorine. As the carbon is forming a single bond, it undergoes sp hybridization and its shape is tetrahedral. And while coming to this, here the carbon is attached to a triple bond. So a triple bonded carbon will always form a sp hybridization, and the shape is linear shape. And next, coming to the next question. Second question: what is the type of hybridization of each carbon in the following compounds? Based on this, you can be easily able to answer this question. In CH3Cl, here the CH3Cl will undergo sp3 hybridization. Here the carbon undergoes sp3 hybridization. It is formed 3 bonds. And next, CH3 taken twice CO. Here the carbon atoms undergo sp3 and sp2 hybridizations, and while coming to CH3CN, here the carbon atoms undergo sp and sp3 hybridization, and in HCONH2, here this carbon undergoes sp2 hybridization. So double bonded carbon will undergo sp2 hybridization, and while coming to CH3 CH double bond CHCN, here the carbon atoms will undergo sp2 sp2 and then sp3 hybridization. So we can be able to answer all these questions based on these 3 points. And next, coming to the third question: how many sigma and pi bonds are present in each of the following molecules? Here, to answer this question, you have to know. With these 3 points, you will be able to answer this question. Here, a single bond will consist 1 sigma, double bond 1 sigma and 1 pi, and a triple bond consists of 1 sigma bond and 2 pi bonds. While coming to this option A, here sigma carbon carbon bonds are 2, sigma carbon hydrogen bonds are 6, and then pi bond is 1. As here only one double bond is present, we have only one pi bond. In this way, you have to check the sigma and the pi bonds in these. And while coming to this option B, here the sigma carbon carbon bonds are 3, sigma carbon hydrogen 6, and then pi bond are 2. Here it is a triple bond. A triple bond consists of 1 sigma and 2 pi bonds. So here the pi bonds are 2. Try this question as a homework. And now coming to the next topic, writing Levy structure. There are here I am taking CH3NO2 as an example. There are two primary Levy structures for CH3NO2. So here we have a carbon surrounded by the 3 hydrogens and the nitrogen with 2 oxygen around it. For the CH3NO2 Levy structure, we have a total of 24 valence electrons. We will form bonds between atoms, and each one of these bonds represented 2 electrons. Let us form bonds. Here totally 1, 2, 3, 4, 5, 6 bonds are formed. So we know that each bond will represent 2 electrons. So here totally 12 valence electrons are used up. And then we will go around the outside of the oxygens to fill their octets. Here the oxygen already have 2 electrons. So to get octet, it should get 6 more electrons. Here the problem is everything has an octet, and then the hydrogens, they have 2 valence electrons, so their outer shells are full. Here the hydrogens also have the 2 valence electrons, and their outer shell are also filled, and this oxygens also got its octet. But here the nitrogen in the center does not has octet. It has only 6 valence electrons. So what we have to do is to share the valence electron from one of the oxygens. So let us take this pair here, and let's take this pair right here and use that to form a bond here. So by forming a double bond, The oxygen still has 8 valence electrons, that is 1, 2, 3, 4, 5, 6, 7, 8. But now the nitrogen has 8 valence electrons as well. And we are using only 24 valence electrons for the total CH3NO2 molecule. So this is one of the Lewis structure for CH3NO2. It is also called as nitromethane. We call it as nitromethane. This is one of the Lewis structure for this CH3NO2. See here, this is the second Lewis structure. You can also draw the structure methyl nitrate as shown here. Now coming to the next topic, calculation of formal charge. Here we can calculate the formal charge by using this formula. Number of valence electrons minus number of bonds minus number of unshared electrons. Here coming to the fluorine, it has 7 valence electrons, and coming to the nitrogen, it has 5 valence electrons. Oxygen, it has 6 valence electrons. Carbon, it has 4 valence electrons. Now let us calculate the formal charge for this methyl nitrite ion. See here, this is the structure 1 and structure 2. Here you have to remember a point that structure 1 with no formal charge is more stable than structure 2 with formal charge. The reason for this is this stability is due to minimization of repulsive forces between the electrons and the overall decrease in energy associated within the molecule. Here you have to remember one thing, that is, lower the charge, stronger is the bond, and thus it adds to greater stability. See here, lower the charge. I mean, when the charge is less, the bond will be stronger. Bond is stronger, and thus it adds the greater stability. When the bond is stronger, it will have a greater stability. That's the reason why the structure 1 with no formal charge is more stable than the structure 2 with formal charges. Now let us calculate the formal charge on this methyl nitrate ion. See here the formal charge on oxygen atom. Let us consider this as oxygen 1 and this is oxygen 2. Here we have already discussed that the number of valency electrons of oxygen is 6. So the number of valence electrons are 6, and here the number of bonds, that is 1, and the number of unshared electrons 1, 2, 3, 4, 5, 6. So totally we get as -1. Here the formal charge on this first oxygen is -1, and the formal charge on the second oxygen atom, again here the number of valence electrons of oxygen is 6, and the number of bonds 3, and the number of unshared electrons are 2. So the formal charge on this second oxygen atom is +1. And next, coming to the formal charge on nitrogen atom. Here we know that the number of valence electrons of nitrogen is 5, and the number of bonds that is 3, and the number of unshared electrons are 2. So 5 minus 5 we get 0. The formal charge on the nitrogen atom is 0. In this way we can calculate the formal charge of any molecule. And next, coming to the last topic, structural representation of organic molecules. Structures of organic compounds are represented in several ways. The Lewis structure or dot structure, dash structure, condensed structure, and then bond line structure. Here I'll give the example of complete structural formula. See here the organic molecules are represented in complete structural formula in this way. And then coming to the examples for condensed structural formula, that is CH3, CH3, ethane. This is ethane. And then CH2 double bond CH2. Ethene, CH triple bond CH as Here there is a single bond, we call it as ane, and here the two carbons are present, so we call it as ethane, double bond and two carbons. If it is double bond, then we call it as ene, single bond ane, and a triple bond ine. So this is called as ethine, and then CH3OH. This is called as methanol. Here CH3 is called as methane, and as the OH group is attached, we call it as methanol. See, these were the examples for condensed structural formula. And next is similarly, if we take CH3, CH2, 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 and then CH3. So we can further condense this as CH3. Here CH2 is repeated 1, 2, 3, 4, 5, 6 times. CH2 6 and then CH3. This is the representation of condensed structural formula, and this is for the complete structural formula. And then coming to the example of bond line representation. See, in bond line representation, we can represent in this way. So the molecules are represented in this way. For example, if we take propane in bond line, we can represent it as it is propane, it should contain 4 carbons. Here, this represents 1 carbon, it represents another carbon. See here, totally we should have 4 carbons, 1, 2, 3, and then 4 carbons. In it means all are single bonds. So in this way, we represent the bond line, we represent the molecules in bond line. For example, if we take cyclopropane, cyclopropane can be represented like this. Here a CH2, here one CH2, and here another CH2 is present. In bond line representation, we can represent the cyclopropane in this way. And next, here the various ways for representing 2-bromobutane. We can represent this 2-bromobutane in this way. To represent this in bond line, we can represent in this way. So 2-bromobutane. Butane in the sense it should contain 4 carbons. So here 1, 2, 3, 4. 1, 2, 3, 4, and 2-bromo. In the second carbon, you should have a bromine. So in this way, we can represent the 2-bromobutane. In cyclic compounds, the bond line formula may be given as follows. For example, if we take chlorocyclohexane, chlorocyclohexane. Here the bond line formula, we can give this as directly cyclo, it should be in a cyclic form, and this is a hexane, so chlorocyclohexane. Here this represents CH2, 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 and then here CHCl. Simply we can represent as like this. And next, I'll give you examples for bond line structures, and then you try it as a homework. Write the bond line structures for these 4 molecules, and I'll give answers for this in the next video. Thank you for watching my video, and in my next video I'm going to explain classification of organic compounds. Please subscribe my channel for my upcoming videos, and if you have any doubts regarding this topic, you can ask me in comments, and if anyone want notes regarding this topic, you can also ask me in comments, and then I'll give notes for this topic in my next video. Thank you for watching.